Thanks for the opportunity to speak and close out the first day here on the lecture series. Today, we're going to be talking about some of the NVIDIA profiling tools that are available on Polaris. And in addition to talking about some of the features and kind of the mindset you might want to get in as you're using these tools, we're going to have a little bit of a hands-on session toward the end where you can actually profile some of your own applications and actually get a hands-on, seeing what it's like to optimize in some of the targets we might look for. So, yeah, my name is Chris Keipert. I'm a solution architect at NVIDIA. I've been at NVIDIA for about 3 years. My background was in high-performance computing, computational chemistry. I was actually previously at Argonne. That's where I started my career after grad school, working on the NW-ChemX project. Continue to really enjoy collaborating with people in higher ed and of course the DOE lab. So if you ever have any questions about GPU programming, right, feel free to reach out to me. And yeah, let's go ahead and get started here. All right, first, so in order to have a well-defined target here, let's talk about what type of programming models we can actually use to target the NVIDIA platform, right? These are the, we've heard about a number of different programming models available on Polaris, but these are kind of the main focus ones that I'm going to focus on here today, right? So, on the right, of course, we have CUDA. CUDA is our low-level, more architecture-specific language, right? It requires some knowledge about the way the GPU works. You're going to be explicitly managing threads, parallel threads on your processor. You can see here without, you don't need to know CUDA to get something out of this this lecture here, but you can see we're marking up our functions to indicate they're running on the GPU. Here we have some idea of kind of bookkeeping about our threads that we're going to use to attack the problem. A little bit lower, you can see the idea here of these explicit memory copies where we're actually copying data from the host side into the GPU's dedicated memory space. And then even the function call, you can see this triple nested caret syntax, which we've seen a couple of times today, right? Which actually indicates the number of threads and how to organize those threads as you're throwing them at the GPU problem, right? So, again, don't need to know the details too clearly here, but you should just know that, hey, we have some semblance of a GPU centric hardware model, right? We're doing things explicitly, and we have to control our data movement in our compute, right? And then in the middle, you have this idea of these incremental portable optimization layers, right? Things like OpenACC, OpenMP, you could even throw Cocos in here, right? The idea of instead of getting here and explicitly marking up our language and targeting the GPU specifically, we're just going to look for sections in our code, functions that we know are low-hanging fruits and maybe performance critical, and we mark them up with these comments that indicate that they should be parallelized, right? This looks like something, right? It's a really juicy loop. It should be parallelized. And then we rely on OpenACC or OpenMP, at either the runtime or at compilation time to generate the parallel implementation for us, right? And that's going to let us target different hardware architectures, maybe even, with a simple flag change, switch between targeting a multi-core CPU versus a GPU, right? And all three of these things are supported on GPU with all of our profiling tools, including the one that actually has a lot of momentum behind it nowadays, is actually accelerated standard languages, right? So the idea here is you have an ISO standard C++ code, ISO standard Fortran code, right? So in some of the later standards here, in the standard languages, they've added things such as the do concurrent loop, right? Which is goes beyond the regular do loop that we're used to in Fortran 77, right? And then likewise in C++, they have a number of stood par parallel algorithms baked right into the ISO standard language, right? So it turns out for a class of algorithms, right, and a class of problems, if you compile with an NVIDIA compiler, just with this ISO standard language, right, the ultimate in performance portability, you'll actually get free implicit offloading into the GPU and the speed up associated with that. I'll also mention I've been spending more and more of my time, even when I'm writing CUDA, I'm writing it in Python, right? So there's a ton of momentum behind GPU accelerated Python, and not just on PyTorch and TensorFlow, but that extends to things like CuPy, Numba, cuNumeric, even JAX, which has really great GPU support. So feel free to reach out if you have any questions on GPU computing in Python. Certainly during our office hours here, right? And all this is going to work on the profiling tools we're talking about today. Okay, so for the next piece, I should mention, right, where do we actually get these compilers? Well, certainly they're available on Polaris, but you should be aware of this umbrella collection of software we have called the NVIDIA HPC SDK. This is about 2 years old, and basically what we did is we took a bunch of pieces that you need to develop and profile HPC software, and we put it under one umbrella here, right? So you've got your support for the various programming models that I mentioned, which is certainly going to include NVIDIA compilers, right? These are, if you've ever used the PGI compilers in years past, you'll be familiar with these, right? Continue to push forward here. Fortran, C++, C, really excellent for both generating CPU and GPU code. right? A bunch of core libraries, certainly our math libraries. I'm sure a lot of folks here are using cuBLAS and cuSolver for those BLAS and LAPACK type operations. And we even include a CUDA-aware MPI, right? So you can use the MPI right from that HPC SDK, whether you're getting that from a container, loading up a module, getting it from the cloud, NGC. And then certainly all of the profilers and debuggers that we're going to talk about today are included under this umbrella as well, right? This is updated and released between 7 to 8 times per year, freely available. So yeah, definitely this is a good starting point, right? You download this, it's kind of the kitchen sink, and you make sure you get all the pieces that you need. All right, so moving into development tools. So 4 classes of categories here, right? So on the top left, we have our standard debuggers, right? That would really the headliner there is CUDA GDB, right? Which is really designed to be GDB-like. It's actually built, it's based on top of GDB, and the idea here is we want to minimize the amount of new syntax and new new APIs that you need to figure out to actually use this thing, right? So me, with experience using GDB, I've used CUDA GDB extensively as well without having to look at the documentation too much there. And then this is also well integrated if any of you folks are using some of the more commercial IDEs, things like NSIGHT Visual Studio Edition, right? We have CUDA GDB integrated there just like you would a standard CPU GDB, right? Then on the profiler side, so you may be familiar if you've done GPU programming for a while, you may be familiar with NVProf or the NVIDIA Visual Profiler, right? Those were tools that we had in the past to profile our applications, and we've since come out with a new suite of tools called NSIGHT Systems and NSIGHT Compute, right? So I'll talk on the next slide some motivation of why we broke that into 2 separate tools and where you would use each of them. But right, we have the NSIGHT suite in addition to the NBTX markup language and a bunch of really great features there for profiling your GPU code. On the bottom left there, we have the so-called correctness checker tools. So this is going to be analogous to valgrind or cache grind, right? The idea of you basically, throw your program in here and it will look through for any errors, things like out of access memory or out of bounds memory accesses, race conditions and whatnot, right? And it's relatively easy to do, right? You plug it right in and you can get some plain text errors spit out that can really help your debugging efforts. And then on the bottom right, as I've alluded to, right, we have excellent integration across certainly the Visual Studio and Eclipse IDEs, right? I mean, I still do a lot of things on Emacs myself, but I think I need to spend the time to get some time with Visual Studio because it's really nice having that the debugger and the profiling tools built right in there. All right, so let's go into the workflows for the NSIGHT tools, right? So as I mentioned, we kind of broke this out into multiple programs a couple years back, right? So thinking of a typical profiling workload, right? We're going to start generally with NSIGHT systems. So NSIGHT systems is going to give, from the name, a systems level view of our application running, right? It's going to show us a timeline of the GPU kernels running, the CPU kernels running. It'll show us any time that it took to transfer data from the hosted device or vice versa, right? It's going to give us that very high level view. We can use it to do things like, hey, maybe look for hotspots in our application, maybe look for really big gaps where we're not doing any computation and see if we can fill those. Maybe look for opportunities to overlap data movement with computation, right? There's actually a ton you can do before even digging into the GPU kernels themselves, right? And in fact, this is where I probably spend 90% of my time when I'm doing profiling is in NSIGHT systems, right? Now, once you've lined out all your data transfers up and you know what kernels you want to attack, right? You know what your bottlenecks are. That's when you move over into NSIGHT Compute, right? So NSIGHT Compute is going to give you a very detailed, low-level information about your kernel, right? You're going to know things like register usage, right? You can even look at the assembly and hotspots in your assembly code. All levels of the memory subsystem, how stressed they're being, right? The SMs. You can even get roofline plots. We're going to go into a bunch of detail here, but again, right? The idea being you only go into NSIGHT Compute when you know you're ready to do a deep dive into an individual kernel, right? And then you spend some time in there, you make the kernel run 10 times faster. Well, that means you need to go back to NSIGHT systems and re-examine your timeline, right? Because that's going to affect everything. If you are someone that's doing graphics applications, actually, I had the opportunity to do get some experience running Omniverse, NVIDIA Omniverse on Polaris recently and render some different frames in there. We also have NSIGHT graphics, so this is used quite a bit for rendering performance, right? So of course, the game engines of the world, but people like PeerView and people that are using scientific simulation visualization software are heavy users of NSIGHT graphics as well. All right, so NSIGHT systems. As I mentioned, this is our high-level, system-wide way to look at our application. It's generally our first stop when we want to start examining an application, either that's already on GPU or even for the viability of GPU acceleration, right? As I said, kind of the headliner piece here is this timeline, and we'll show some more zoomed-in pictures a little bit shortly here. But right, we can look at the CPU threads, the GPU threads, what the OS is doing, data transfers, and again, right, we can start looking at gaps here and start lining things up and get a lot of, find where we need to focus our optimization efforts. Another thing I want to mention is that these NSIGHT systems and NSIGHT Compute are available as a GUI, like a graphical interface, and as a command line version. And generally, especially for supercomputer centers where you got to hop onto a compute node, I generally stick with the command line interface, right, and do as much as I can over the command line. But a typical workload is if you do want to open things up in the graphical interface, you would actually run on the command line to collect a report, and then you would SFTP or SSH or move that over to your local laptop or local development machine, and then you would launch the GUI there, right? So the actual GUI itself, it can run on Linux or Windows or Mac. You don't need a NVIDIA GPU at all, right? It's just kind of a front end to examine the profile if you're not getting what you need out of the command line. Okay, right. This kind of gives a little bit of an overview of what types of information you might see posted here, right? So again, there's a lot of information about from the CPU side of the coin. We can see a lot of CUDA API traces, right? We can see kernels running. Here's some tensor cores utilization here, data transfers, and even down here you can see this is an instance where it was ran on a multi-GPU system, right? So first look at this, my first impression would be that is way too much information, right? It looks like some type of spectrogram, right? I mean, how are you going to figure out where your bottleneck is from here? So um, a big part of the workflow of using NSYS, and as soon as you get inside, is to start filtering down and zooming into areas of interest, right? The sections that are most relevant to you. And this can be tough sometimes, right? Especially if you imagine like an iterative method, right, where you're maybe doing 100 iterations. It might be challenging to find, right, what's repeating 100 times? Where's the boundary point? But furthermore, a lot of these GPU kernels are executing so quickly that you have to zoom into the sub-second time frame to actually see your runtime, right? Furthermore, as you're zoomed out and you see kind of these graphs that correspond to utilization, right? As you're zoomed out, these are just time averages, right? So what looks initially like a valley or a lower utilization, if you zoom in a little bit more closely, you'll often find discrete gaps, right? Again, those are averaged together, so you'll find that there are gaps. And again, that's something that you need to take a look at and see if, why is there a gap there? Is it something I can address, right? Are we waiting on some memory? What's going on, right? So one of the most useful tools for making sense out of these profiles is NVTX, right? So NVTX is essentially a markup language where, as opposed to relying on all this soup here and trying to figure out the relevant sections of your code, you can actually instrument your code directly with labels, right? So this is an example for the VMD visualization software where this programmer had instrumented the code, sections of code with these labels, right? And now these appear as NVTX labels in our profile on the bottom. So it's very easy to look up and see how those correspond to actual execution, right? So I highly recommend using NVTX as soon as you can, right? Generally, people will leave NVTX in the code and kind of leave it as a debug option, whether or not you want to emit it or not. But anytime you're doing debugging, NVTX makes things much more easily done. All right, so another really nice feature that was a little bit newer here, and what I think is what we need to see more and more in these profilers is expert systems, right? So this is the idea of providing more plain text recommendations on what type of optimizations you might want to look for, right? I say no matter how much time you spend in a profiler, even if you're an expert in tuning these things, anytime you move to a new tool, there's at least a few hours, right, upbringing just to kind of figure out where all the buttons are, right, if not a few days, right? So the nice thing here is, you drop in, you run your program through, and you're going to get this plain text indication of, some optimization targets to look for, right? So this is a very common example where somebody's trying to do an asynchronous CUDA mem copy, but the data on the host side is allocated in a pageable bit of memory, which means that it's actually a blocking operation, right? So it indicates that you should perhaps consider allocating that data on the host side in pinned memory instead, right? So, these are good ways just to kind of distill out the important things out of your profile here. Okay. Another nice newer feature is this multi-report tiling, right? So in the hands-on session here, we're going to be focusing on just a single GPU. But of course, I know you folks, and I saw some of the applications you're all running, right? You're running many, many MPI threads with many, many GPUs, right? So with this new multi-report tiling, you can actually open up multiple reports in one interface and have them overlapped on the timeline, right? So, they're based on the same wall clock. It removes if there's a little bit of jitter upon the initial execution of the program. And now you can see, right, multiple MPI ranks, what multiple GPUs are doing in concert, as opposed to having to open up multiple instances of the interface here. Okay. So we have some Polaris specific commands that we'll run through on the hands-on, but just as a general kind of first glance way to start profiling with NSIGHT systems, right? So we have this NSYS profile -o report that's going to generate, of course, a report file. In more recent versions of NSIGHT systems, that report file will have the suffix QD report. But in some older versions, you may see this so-called NSYS report, but they're essentially the same thing here. The stats equals true flag, this is going to print some summary statistical information right on the command line, right? Some high level information like the SM or core utilization, even the memory utilization. So I generally keep that on just so you can kind of get a sneak peek of how things are running before you load it into the user interface there. And then finally, of course, you need to invoke the actual application, right? Again, you take that file if you want, right? Maybe you have all the information you need from stats equals true, what's printed off on the command line. But if not, you generally are going to SFTP or however you want to move it off, move that over to your local system and open it up in our NSIGHT systems user interface. Right. One note on when you are using MPI. So there's always this idea of, do I put the NSYS outside of the MPI run, or the MPI outside, right? And generally, as a general rule of thumb, I would say generally put the NSYS inside, nested inside the MPI run command, right? In this example, we would actually have 4 separate NSYS profiles created, one for each rank. Right, and if you'd like, in terms of to make it easier to collect all the reports and whatnot, you can even use that -o flag and give the report a name that is based off, for example, the MPI rank, right? You can use like a environmental variable and throw it on the end of that report, and read in multiple reports at the same time on the user interface. All right, a couple gotchas on profiling DL models that you should be aware of, right? As we have more and more people profiling these DL tools, right? In the past, we actually did have, we in NVIDIA had a DL prof profiler, which was dedicated for profiling DL workloads and whatnot. I know, right, there's things like TensorBoard and whatnot that are really great as well. But a couple things to be aware of. First of all, these PyTorch, any of the DNN layers, the annotations are disabled by default. So if you are actually wanting to profile at the level of your neural network there, then we have this simple torch autograd flag that you can throw on there to emit the NVTX. And then by default, right, you'll get all the NVTX spit out in the profile, so you can start analyzing it. Right. If you want to start maybe instrumenting sections of your own code that you're doing within the PyTorch framework, there's also this nice convenient Torch CUDA namespace NVTX. And we're actually going to see shortly when we're adding NVTX to some of our own code. And this is an identical API to what you would do with native CUDA as well. Right. TensorRT backend, if you're using TensorRT for any of those inference workloads and whatnot, that's already annotated for you. Right. And then moving over to TensorFlow, those annotations are enabled by default if you're downloading TensorFlow from the NVIDIA containers, right? That means if you go to like the NVIDIA NGC container repository, where we have a bunch of optimized containers for PyTorch and TensorFlow and hundreds of different open source applications out there, right? If you consume your TensorFlow that way, then by default those annotations will be enabled. So you can go ahead and throw that flag on there to disable them if you're looking at production. Again, not much overhead from NVTX, but we're running on HPC and GPU accelerated systems for a reason, right? All right, so moving on to NSIGHT Compute, right? As I mentioned, this is for once we have our CPU and GPU is working well in concert. We have all our data transfers how we want them. Now we're ready to start deep diving into an individual kernel, right? So NSIGHT Compute, you can see here on the right, right? A bunch of detailed information. We can see this SOL, which refers to speed of light. So how good are we doing compared to what the peak of the GPU? What's possible, right? We can get all these different metrics that are taken, and you can use them to compose even more complex metrics. We even get some source and assembly information down here where we can even look for hotspots. Same idea here, right? Much like NSIGHT systems, right? If you can get away on the command line with the information, that's great. Easy to do on the compute node on Polaris. But if you do want to go in there and either analyze things visually, or even if you want to take advantage of a visual performance model like a roofline chart or a memory analysis chart, then you can go ahead and load it into that GUI. Again, no matter what operating system you have, just throw it on your laptop and you're good to go. Okay, so when you first jump into an NSIGHT compute, into the GUI, this is what it's going to look like, right? You get these targeted metric sections. These are the types of things that are generally spit out by that on the command line, right? So if this is all you're interested in, you generally don't need to dive too much further, right? You're going to get a customizable presentation of your data. You can see here we're just simply plotting the SM memory utilization, right? Which, a bit under 50%, not too bad. And then much like the NSIGHT systems, and perhaps even more mature, there's also this built-in expert analysis or expert guider, right? Which will give you, again, plain text information. Hey, this looks like a bottleneck. Hey, this looks like something that you should address, that needs some attention, right? So you can get pretty far just with like the top half of your screen on there. But if you start scrolling down further, you're going to see a bunch more analysis tools and different charts here, right? So this is actually a memory workload analysis chart. So if you think of the GPU, right, not that we're going to get into too much detail today, but there's a relatively complex memory hierarchy, right? We have global memory, local memory, texture memory, surface, shared, not to mention the cache of the CPU itself, even the DRAM, right? And as we're transferring data and arranging things across our supercomputer here, right, it's useful to know what our traffic looks like, right? What our cache hit rate looks like. And everything here is in very neutral green and blue colors. But if you load in a profile where you have a really bad hit rate or something like that, these will actually light up red and say, give me attention, right? So it's a good way just to see, again, are things moving as expected. Okay, and then as I mentioned, right, going even further, we can actually do some analysis and correlation between the PTX and the SAS, which is like the assembly or machine level code that is generated. Again, people typically don't write at that level, but there's actually a sampling metric taken here, right? We can see how long we spent in a given line of code or a given piece of assembly, right? So I mean, that's clearly very useful for identifying hotspots in your code. With the caveat that just because you have one line of code that you're hitting on very heavily, it doesn't necessarily mean that one line is your optimization target, right? Very often it requires some restructuring around that line of code. But that being said, it brings us into the low-hanging fruits at least. Okay, and then another one that I wanted to mention is this occupancy calculator, right? So if people have been doing GPU programming for a while, you may be used to the occupancy calculator being an Excel document on NVIDIA's website, right? That you plug in some of these numbers and get something spit out. Well, this has actually been integrated now into the NSIGHT profiler here, right? So occupancy, it gives you a feeling for, do I have enough active work, right? Do I have enough blocks of work in flight? A modern GPU can easily manage on the order of 100,000 parallel threads all operating at once. And it turns out that we actually want to keep a lot of threads just because of the architecture of the GPU, right? It's very good at swapping between tasks, right? And if there's any stalls with the SIMT architecture. So we want to have a lot of things in flight, and our occupancy is going to give us a feeling for how well we're doing at parallelizing our problem here. Okay. Then we also have, as a newer feature, this hierarchical roofline, right? Which is probably the most successful performance model, right? It's been out for probably on the order of a decade now, right? And the idea here is, I'm sure many of you have already seen these before, but it's a way to see how good our kernel is doing against the theoretical limits of the hardware itself, right? So what we generally do here is we have this angled line, which corresponds to the bandwidth, memory bandwidth, and it can be DRAM or it can be L2 cache, L1 cache, whatever, right? We have different lines for that. And then on the top where we have this horizontal line, that corresponds to the flop or the computational throughput roofline of the GPU, right? So essentially for a given kernel, we can measure our so-called arithmetic intensity. That means for a given byte of data that we're moving, how many flops, how many operations are we actually doing on that, right? And if we're in this region, right, underneath any of these bandwidth rooflines, that indicates that our application or our kernel is in a bandwidth bound region, right? So we're limited by the memory bandwidth. Where if we have a higher arithmetic intensity, right, in this region where we are under just the performance roofline, that indicates that we're limited by our flop rate, right? So it's a really good way to kind of see what you need to target, right? If you're bandwidth limited, maybe you need to look at memory access patterns or whatnot. And if you happen to be so lucky to be on one of these rooflines, well, you got to wait for the faster GPU, right? NSIGHT compute, yeah, it's pretty similar for NSIGHT systems in terms of the command line here, right? So we have moved from NSYS to NCU. Sorry, the font there is a little strange, but that's a K there. So you have this -K my kernel. That is a flag or a filter that says to filter the kernel called my kernel, right? So of course, there's some overhead associated with running these profilers, right? So if you have an application with 1,000 kernels in it, and there's only one that you care about, right? You probably want to filter all those out. So I'm generally always listing the name of the kernel that I'm interested in with this filter here. You can use regex as well if you'd like, if there's multiple. The report name, right? And then the invoke the actual application, right? So this is going to give us, again, one of those enku rep files, a little bit different than the qt rep we get of NSIGHT systems. And right, we can load those into our NSIGHT compute UI if we'd like. So yeah, pretty similar workflow there. All right, before we get into a bit of this hands-on session, let's take a quick look again at this CUDA GDB and a couple of the other tools, right? So a reminder, this CUDA GDB, right? It's a unified CPU and GPU debugging, right? So you can use this. It's built on top of GDB, so it uses the same CLI arguments for stepping through the CPU side of the coin, and certainly, adding that GPU support where we have both local and remote connection support. And then, as I mentioned, a little bit more detail here on Compute Sanitizer, which I highly recommend to use, especially if you're not using, for example, like STL containers for data and whatnot. Right, we have 4 different collections of tools in here. Memcheck, again, for those memory access and leaks, right? Maybe you did some out of bounds memory accesses, or maybe you forgot to clean up or finalize a cuBLAS instantiation, right? Race check to look for any of these race conditions. Init check for these uninitialized global memory, and then sync check looking for any of these thread synchronization issues, right? So if you're just racking your head, and sometimes these errors can be very subtle, right? I mean, this is these codes as you're running on a CPU and GPU at performance. Sometimes I just go ahead and just run through memcheck and race check and just make sure everything looks sane, right? And give us very plain text hints when things are not lined up properly. Okay, and then again, if we have any Visual Studio users out there, so I know they have this Visual Studio Code Edition, which has this whole app store-like interface where you can download plugins. So we now have an NSIGHT Visual Studio Code plugin, right? So you can see here we have all of our variables and our stack and registers for the actual GDB itself. You get auto completion and syntax highlighting for any CUDA program as well. So yeah, if probably a lot of people here are sticking with Emacs or VI, but this is a good thing to check out as well. All right, so we have some additional resources if you're curious about learning a little bit more, right? So we actually just had a GTC GPU technology conference session 2 weeks ago, right? So NVIDIA, we put this GTC on twice a year, which it's our opportunity to first announce any of our new products or any of our new updates, but also we have a ton of talks from external folks, a lot of people from academia, national labs, different industrial locations who will come in and talk about what they're doing on the GPU, right? So as part of those sessions, we very recently had this briefing on some of the new features in CUDA, some performance targeting tips when you're looking at taking advantage of the new tensor cores, right, for that really dense linear algebra acceleration. And then we even have some labs that you can go in and view. These are all pre-recorded sessions, all free to access, and see folks actually applying some of these tools, right, the engineers who made these things to some real problems, right? So I highly recommend checking these out, and as these slides will certainly be distributed to everyone here. All right, so let's spend a little bit of time in this hands-on section here. So folks are free to follow along and work on it as well, but I'm going to be working through it as well, so anyone can see it who maybe isn't on Polaris right now. So this, first of all of the data for this lab, it's a collection of I believe 7 source files. You can find it on this eagle on the luster here. I just copied it over this morning into a Jacoby folder. Everyone should be able to grab a copy of that. And I'm not a discrete grid type person, right? I'm a quantum chemistry person, so I'm not gonna try to, or hopefully I do justice here. But what we're doing is we're actually solving the Laplace equation using Jacobi iterations, right? Jacobi solvers are very commonly used, right? Iterative solvers. And long story short, what we're doing is we have this grid of discrete points, and for a given iteration, in order to get the value at that point, we actually want to take the solution at the previous iteration, okay, and take the average of the 4 corners around the point of interest. right? For example, in order to get Fij, we need to look at Fij from the previous iteration, and we need to look at, I move 1 in the I direction, minus 1 in the I direction, plus 1 in the J direction, minus 1 in the J direction, right? So we're taking all 4 points around our discrete point, and then we're taking the average of that, right? And if we keep doing that over and over and keep propagating this equation and keep plugging it in, we're eventually going to get we're going to have some type of equilibrium, and we're going to reach some stable point, which we can continue to check with this error value and keep going until more and more iterations until we're pleased and below our tolerance there. So looking at the pseudocode here, right, it essentially consists of setting these some initial conditions for these array values, right? And then you can see this is kind of the core of the problem itself, right? Where we have this nested loop, and again, we're taking values out of the old solution, and we have a couple just additions and multiplications here, not too intensive, right? Computing the error, and then once we solve for the current iteration, we have to go ahead and take our current value of f and swap it out to f old, right? Because remember, we're going to use it for the next step, the next iteration. So how does that look? Did we switch over to 2 terminal windows? Or are you still seeing my, okay, excellent, great, cool. So as I said, right, this is maybe screenshot it really quick if you want to grab some of the files. I just made a local copy here, right? So we have 7 different files, and then I have an instructions page, right? So listed it here. All right, and then I have the, also just for completeness sake, I have the qsub command that I'm using to get an interactive queue, right? So I just copied what Yassi had wrote earlier and then threw on the -I at the end there, which is going to give us an interactive session. All right, cool. All right, so I'm on the system. Let's move over to the Jacobi folder. And all right, we should check NVIDIA SMI. Yep, looks like we're on compute node, right? We got 4 A100s with 40 gigs each. All right. So first, let's take a look at our baseline code, right? This is our Jacobi, and again, we don't need to worry too much about all the details. If you look at just the function names, we're probably close enough. Let's drop down here to main, right? So we're initializing the error to some large number, so we don't converge on the first step, right? This is kind of our outer loop where we're actually checking the error of whether it's below the tolerance or not, right? Here you can see our Jacobi step. That's that nested loop that we mentioned, right, where we're taking the average of the 4 neighboring corners. And here you can see we have a separate function called swap data, and that's actually going to swap out that f with f old, right, as we mentioned before. And that's pretty much it, right? We're going to print out every 25 iterations or so what the error is looking like, and yeah, pretty straightforward. Again, don't get into the details or devil's in the details, but this is a CPU only code right now. So let's just go ahead and compile it. I'm using NVC++, which is the NVIDIA C++ compiler, right? Again, this is a CPU code, right? So there's no GPU in there at all, and it's compiling just fine. Let's go ahead and run it just to see what it looks like. That was really fast, wasn't it? Still on the CPU. Took well under a second for 550 iterations. All right, so we want to profile this thing, right? A reasonable first step is to add NVTX, right? Recall that NVTX is our way to kind of mark up sections of code or functions such that in the profile, right, they'll kind of be broken out into their own distinct sections here, right? So it's pretty self-explanatory, right? You can see we're doing this range push and we give some descriptive name, right? Function name is a good one. And then we do this little NVTX range pop when we want to close out one of these sections here, right? So we've marked up pretty much everything. We have it on the memory allocation, the data initialization, right? It's not necessarily a bad thing to be verbose here, right? And then of course we have the Jacobi step and the swapping of the data. Okay. And again, all these instructions again are on that instructions.txt, right? I'm copy and pasting them because they're pretty long here, but okay, so now what we're going to do, right? We've moved over to that 2 NVTX. The only thing we did is we added NVTX instrumentation to our CPU only code, right? Now I'm switching over to using the NVIDIA compiler as I've added these NVTX extensions, right? So just line by line here. Can I zoom in? Probably not. Let's see if it works. Yeah, cool. All right. Yeah, so line by line here, right? NVCC invoking the compiler. This arch equals SM80. So this refers to this is used in order to target the Ampere architecture, right? As we go through different GPU generations, different GPUs have different capabilities. So this SM80 corresponds to the Ampere A100s on Polaris. This -O, that's going to produce, as we mentioned, one of those, or the actual binary itself. This -XQ. So this is a little bit devil in the details, but essentially what this is doing is by default, NVCC is going to be invoked on .cu files. .cu is the default extension for a CUDA source file. But you see that we're going to be using a C++ CPP file. So this basically says, hey, don't limit it just to .cu files. Then right here, as we've added these NVTX instructions, we're now linking this additional library. Right, and then finally, try it out. Yeah, and sorry, I'm getting some word wrap issues, but that does have a CPP extension there. I'll try this again. I think somebody told me this. Maybe. All right, so it compiled, right? We can try running it if we'd like. Okay. A little bit slower with the additional instrumentation. Okay. But now that we have that NVTX, let's go ahead and profile it, right? We're doing this on the command line. Oh, sorry, I'm going to scroll up here just or show the command again, right? NSYS profile, stats equals true, right? Again, that's going to give us that command line information, right? This is going to give the report name. This -F right here, this actually means force overwrite. So it means if there's an existing report file with that name, then overwrite it, and then right, invoking the actual binary itself. Okay. So you can see here, right, we have our typical iterations printed out, and then we have some information down here. You can see, right, that there's no GPU code right now, right? I mean, most of the actual things that are going to be traced are like these OS or low-level C functions like put C. But we can see down here we have this, we've broken things again into our NVTX ranges, right? And this is already providing useful information. We can see that we're spending around 78% of our time in that Jacobi step and a relatively smaller amount of time in that swap data, right? And the other ones are kind of, negligible, right? So kind of as expected, the majority of our computation time is spent on the Jacobi step. All right. So next, as we're looking to port this code over to GPU, right, a natural thing to look at is using so-called unified memory, right? So let me just open up two of these if I can. Hopefully this isn't, yeah, like I said, the Emacs on the system for some reason is giving me a headache, but okay, well, essentially what we've done is we've replaced our traditional malloc calls with this so-called CUDA malloc managed, right? Remember, we had this broken out area here for this allocate memory function, so it's really easy to work in here, right? We moved over from traditional malloc over to CUDA malloc managed. Now, this CUDA malloc managed is our so-called unified memory, right? So essentially what it means is any data that you allocate here can be used on the CPU or the GPU. And the actual program is going to automatically handle any migration from the CPU to the GPU or vice versa, right? So in this way, we have a single virtual address space to play with, and it simplifies programming quite a bit here, right? So we've added this CUDA malloc managed. Keep in mind, we're still not doing things on the GPU, but there's no reason we can't use managed memory on the way, right? So we'll go ahead and compile that. Run it. All right, so yeah, so now we have that allocation broken out. So you can see we have an idea of this. You can get a feel for like kind of the overhead of the CUDA runtime API here, right? So on the order of well, under a second here, right? Not too much additional overhead added, but now that we have everything moved over to unified memory, we can easily start moving into start moving into our next problem here. So this is really just for some reason just giving me all right. So a next natural thing to say is, sorry, folks. I'm gonna go ahead and compile this one. All right. So a next natural thing to notice here would be that, hey, this is running really, really quickly, right? I mean, this is taking well under a second to do 550 iterations. Is this necessarily going to be a good target for the GPU? right? And the answer is probably not, right? Because if we think about the overhead of moving data over to the GPU, even if the GPU can compute it much more quickly, the additional data overhead is really going to quickly eat into our any speedups we see here, right? I mean, this is just running so quickly. So this is very common. Very often when you're looking to port a CPU application, you need to think about increasing your problem size or exploring maybe a more complex problem, right? So it's pretty straightforward to do here, right? We can go ahead and just increase the problem size. So on this bigger problem here, oh my gosh, it's still not working. Okay, so let's try this. Yeah, so I just ran the head command. You can see that we have this n, which defines the problem size. I just cranked that up. I think it was like 64 before. Yeah, so I cranked it up from 64 to 2048, made a much bigger problem, right? And now we can start running Jacobi step 4, still on the CPU. Okay, of course it's going to be slower, right? Yeah, last I checked, I think this was on the order of 30 seconds. All right, yeah. Yeah, so we increased the problem size and now we're going from, well under a second. Now we're in the 30-second range. That's a little bit more feasible for GPU acceleration, right? So next, what we're going to do is actually the codification, right? We're actually going to first try taking that Jacobi, which is, again, our bottleneck in our code, and port that over to CUDA. Let's see if this works, if I can open it. I can't. Yeah, this is tough. Yeah, it was working a lot better earlier. So yeah, we don't get our nice syntax highlighting, unfortunately, but that's all right. We can at least read it. Okay, so you can see here, again, you don't need to worry about the details too much, but essentially what we've done is we've taken that Jacobi step, we've marked it up with this global identifier, which indicates it's a GPU device function. Here we're doing some bookkeeping. Remember that we're going to throw a lot of threads at this problem, right? Thousands and thousands of threads. So we're giving each GPU thread an equally sized chunk of that total Jacobi problem to work on, right? So each thread is going to be marching through its own section here. You can see here we still have our, our fold and our just creeping in the index there. And then at the end, in order to compute the error, since we're doing this parallel now, we actually need to use an atomic add into that error as all of these threads. We don't want them all trying to access that at the same time and have a race conditioner there, right? So not too many modifications to the function. This is a pretty straightforward case. And now we're running on the GPU. So I'm going to compile that and run it with NSYS. All right, processing. So we can see already that it's around twice as fast. Probably not what we were looking for, right? That's a little bit disappointing. We're going to dig into some of the reasons why, right? But we're down to about 17 seconds. But scrolling down to the bottom here, the other thing you'll notice is while it certainly made the absolute cost of that Jacobi step cheaper, it also greatly increased the cost of that swap data, right? So you can see our total time here. We're up to what, 11 seconds, where in the past we were. It's probably way up. Oh. Right. So we're having a down to swap data, right? So we're increasing from around 3 seconds to 11 seconds just for the swap part, even though the Jacobi iterations are much faster. Okay, and the reason for that, maybe some of you folks have already figured out, right? As it turns out, so we moved the Jacobi iterations over to the GPU, but we left the swap function on the CPU, right? And that means that if you actually look at our unified memory operations, we need to move the data over to the GPU when we do our Jacobi iterations, and then we have to move it back to the host side to do the swap function, right? So that additional data movement right, is kind of eating and really limiting what type of speed up we can get here, right? So a natural way to approach this would be, okay, well, maybe we can do some prefetching, right? So as we're computing those Jacobi iterations and finishing them, we can prefetch, right, and move things back onto the host side, so we can start running the swap function. But another option would be to just take that swap function that we had previously and port it over to GPU, right? That's kind of the ideal case. If we can get everything running on GPU, we're certainly going to minimize those data movements, right? So the next step here, we have moved this swap function over to GPU. So again, not too complicated. You can compare to the previous version of the function if you'd like there, but right, same idea. We're assigning different threads, different equally sized chunks of problem through this Jacobi iteration, right? This is chunked into 32 by 32 blocks, in fact, giving everything a equally sized problem to work on and crunching through. Let's see how it affects our performance. Right, compiled it, profile. All right. So, well, this looks good, right? Our Jacobi is on top. We kind of expected that, or we kind of want that, right? You can see our swap data, now that we moved it to GPU, is all the way down here, right? It's almost negligible. Our total runtime, again, we could try this without the profiler, but we've dropped it down from, you know, our original 35 seconds down to about 3 seconds, right? So at this point, I would say, okay, I ported things over to GPU, right? Certainly, I need to start looking at the kernel to optimize things further, right? This is kind of a nice. We've already made quite a bit of progress just staying completely inside NSIGHT systems. Okay. All right. Now, let's move over to NSIGHT Compute. All right. So as I said, we're kind of happy. We're kind of happy with the high-level view, right? We have this NSIGHT systems view of our application, and we're ready to dig into the kernel. All right. So let's. Yeah. Again, this isn't working. But you can see it. You can see the command here on the right, right? And NCU launch count 1. That actually means we're going to profile just one invocation of the kernel, right? You can imagine running these things many times to get statistical averages, right? This is kind of in the weeds here. You can see as well that we have this -- kernel name flag, right? This is, I mentioned earlier, a way to kind of filter out which kernels you actually want to measure. We're also using this export command, which is going to export that Jacobi step 6 as a NSYS or NSIGHT compute report file. Force overwrite, which is the same as that -f flag, and then invoking the actual application itself. All right. Now in this case, as we have exported to this Jacobi step 6 report file, we're going to go ahead and import. That's what I ran here. See this enku import. We're importing this NSIGHT report, and some of this information should look pretty familiar to what we saw on the graphical user interface, right? We can take a couple quick looks here and see. Well, let's see our memory utilization percentage. That's like our DRAM and DRAM throughput are very bad. You know, our compute SM percentage is, you know, very well under 1%, right? You know, this is when you see this really low DRAM throughput here, that's often an indication that you have some type of memory access problems, right? So we can dig a little bit further on this, right? That being said, for the Jacobi kernel, we're already operating with these 32 by 32 thread blocks where we have these 2D grids of data. It can be rather complex to try to see if our memory, if our arrays and our layout in our arrays is mapped well to the way that we're approaching with the threads, right? So what we may want to do alternatively is even take a look at the more simple swap data function, right, which has the same memory access pattern, but it's a little bit more straightforward. Okay. And here we get a little bit more information, right? So the first kind of smoking gun here is we see there's these warning for these uncoalesced global memory accesses, right? Generally, right, so far we've been accessing just the global memory on the GPU, which typically means uncoalesced accesses. Here we can see that they expected 523K sectors and got about 8 times that, right? Anytime I see that 8x number, right, it's indicating some type of striding issue, right? It's very commonly. Let's see. Another thing that you'll notice get up to the top here, is that our L2 cache throughput is very, very high, right? That means we're heavily utilizing the L2 cache. And that again kind of corroborates the issue that we're having an inefficient access pattern, right? Because we're kind of doing a lot of caching and caching that data as much as we can in L2 to kind of ameliorate, get around the issue that we have with the actual access pattern, right? So, right, bad access pattern, the L2 and utilization is going to crank up there. Okay. Now, I know it's easy to, after the fact, tell everyone what the problem is with the application, right? Of course, several maybe minutes or hours later, after looking into this a bit further, you may notice some issues here with the striding, right? So, okay. So again, we didn't get into details too much, but at the very, very top of our program, we define this the way to basically take a 2D index and march it into our array, right? So it's a way to map our 2D index into the array itself. But the problem is in a CUDA device, the so-called X direction is the fastest moving direction, right? So through the threads, right, we have a 2D block of threads in the X and Y direction. We're actually not moving in a contiguous fashion, such that every thread has to skip 8 data elements. So if we just simply swap around and move, if we just change that definition there, and now move such that we have the X, or sorry, the X is in the non-contiguous moving direction. Let's go ahead and see how that impacts our final performance here. So compile it. Run it. Okay. And you can see we got rid of our issues about the uncoalesced memory accesses and global memory there. You can see our DRAM throughput increased quite a bit. Our compute utilization increased quite a bit, right? We're still, we reduced the time a little bit here, but that clearly took care of that issue in terms of the memory accesses. So the next step here, right, would be to start looking maybe at the Jacobi iterations themselves, right? We could even take another look at MSys. We would see that the Jacobi step is back to the top, right? We might want to take a look at, for example, that atomic add instruction that we had, right? Recall that we had the atomic add for the error, where you might have a lot of threads kind of trying to access the same data element, right? But there's a lot of places you can go further here. But really, I hope this kind of gave you a high-level view of not a template, not prescriptive of how you might approach your own problem, but kind of some of the information we can get out of these profiling tools and how we start applying that back to our problem to figure out our optimization targets. Right. So, in the office hours this afternoon, my colleague Oded and I are going to be available if you have any specific questions about the profilers. If you want to maybe take a look at a profile of your own application, maybe even talk more about multi-GPU profiling or multi-node profiling. We're open for whatever topics you want to talk about. But that being said, yeah, I hope this sets everyone on a good step for getting really nice performance out of the Polaris system.
Thanks, Chris, for that detailed walkthrough of the profiling tools. That was great.